Good afternoon, everyone. It's my great pleasure to introduce Han Cheng Lie from the University of Potsdam. Han got his PhD from 2016 from the Free University of Berlin, and he remained at the Free University of Berlin for a few years as a postdoctoral researcher. He then moved on to the nearby University of Potsdam, first as an open topic postdoctoral fellow, and then recently from February last year as a junior professor in uncertainty and quantification. And today, he will tell us about his work on stochastic optimal control and importance sampling for diffusion processes. Thank you, Han.
Thank you very much, Xiaocheng, for inviting me. Thanks to the organizers for this opportunity to speak about this. And thanks to all of you for being here. Let's begin. So just before I go into the slides properly, if there is something that you want to ask, please feel free to interrupt. If necessary, I'll just skip some things if we don't have enough time. But if something's not clear, just ask and just unmute yourself and ask. Okay, great. So let's just start with the motivation. The motivation for this work, it comes from molecular dynamics. So some of you might know already that in molecular dynamics, a key idea is the concept of a molecular conformation. So here is a ball and stick model of N-pentane, which has 5 carbon atoms and 12 hydrogen atoms. So that's a total of 51 degrees of freedom, 3 spatial coordinates for each atom. And this is a very simple model of a very simple molecule to treat with, to understand or to analyze using molecular dynamics. What's interesting about N-pentane is that it's somewhat small. It's not a very big molecule, but it's large enough to exhibit some interesting complex behavior. So one of the important things about N-pentane is that you can basically have rotations around some of these bonds here. So this is one conformation. It's kind of arranged in a line. The carbon atoms are arranged in a line. And now what you see is another conformation where around one of these carbon-carbon bonds, basically the group of atoms has rotated. So there are other conformations, but this is the most stable one. And you can rotate around one carbon-carbon bond to get another conformation. And you can imagine that there are other ways that you can do this as well to get other conformations. So what's interesting about these conformations are that transitions between them are rare. As you know, usually molecules they don't exist in a vacuum, at least when they're interesting to us for biology or chemistry. You have usually a molecule in some heat bath, so it's immersed in a whole collection of other molecules, such as water. And what happens is that oftentimes, because of these interactions between the heat bath and the molecule that you're interested in, the molecule can transition between different conformations. So what we see here is basically a short trajectory segment shown in blue. Actually, what you can't see is that this is a whole bunch of blue dots, and the time step is so fine that it just looks like it's just a line. And we start basically in the center. The angles are torsion angles, which is basically an angle of rotation around these carbon-carbon bonds. And let's say we've started our molecular dynamics simulation, which is a simulation of how this molecule is behaving in some heat bath. We start it in the middle, so roughly at torsion angle equal to pi for both. We're measuring the angle in radians here. So we've started the simulation, and it kind of wobbles around values between both pi and pi for torsion angle phi1 and phi2. And we keep doing this. So the simulation continues, and basically you see that the trajectory spends a lot of time in a ball with center at pi. And we keep doing this until eventually it jumps to another region of this torsion angle space. And when that happens, what's actually happened is that you've had a rotation. So basically, this is the rare transition that we are interested in statistical mechanics, in biochemical physics, things like this. So basically, changes between a conformation of this form and a conformation of this form. And of course, this is specific to N-pentane. If you look at more complicated molecules like proteins, where you have thousands of atoms, and you still have basically the same idea. There are regions in your state space where the system spends long times. And what is really interesting are the transitions between these sets where the system spends long times. And we're interested in these things because they often are key to chemical reactions that underpin life, whatever. anything you want. Whenever there's a cell or an enzyme, there's something is like this is happening. Yes.
May I ask, as you said, long time, can you tell me how long?
Okay,
I never run this, so I just curious.
Sure. So in molecular dynamics timescales, so in simulations, when you actually simulate a molecule like this, oftentimes you set the time step. So let's take it, suppose you're simulating or integrating a differential equation, your time step is maybe on the order of femtoseconds, which is really, really small. But the time scale required for some of these rare transitions, especially when you're looking at proteins, for example, that can be milliseconds. So you're talking about really large order of magnitude difference. You have to wait a very long time. You have to integrate your dynamical system for a very long time to observe just one transition. And that's if you're lucky. Does this answer your question?
Yeah, thanks.
And this is why these transitions are rare. Unfortunately, they're the transitions which are really important to people. So we want to understand them better. So this is just what's happened when I've run a trajectory for a really, really long time. And what you can see here is that this trajectory. Sure.
Yeah. Actually, I'm just curious. Like when you look at this kind of this transition path, do you know these two kind of metastable states in advance or not?
Sometimes a priori you don't know, but oftentimes you do know. So it's a bit of an art. It's not always completely data driven. Sometimes it's well, I guess ultimately it is data driven, but sometimes you use knowledge from people who actually have worked with X-ray imaging of the stable conformations of these molecules to get an idea of, okay, here's a metastable set, or is this a metastable set that we haven't observed in nature, for example?
Yeah, because I would imagine that it would be much easier if you know this state, kind of these states, right? So
sure.
Yeah, in that case, it's more like I mean, optimization problem or optimal control problem. But in the case like you do not know these two kind of to any states in advance, then it'll be much harder.
Yes, that's true. Fortunately, in many cases, if let's say you have a reaction, a chemical reaction that you want to study, then you know a priori what metastable sets you're interested in, and so therefore you know which transitions you're interested in looking for.
Thank you.
You're welcome. Thanks for the question. So this is again just basically a longer trajectory of N-pentane, and you can see that the trajectory spends really long times in this conformation, this, and there are 4 conformations where it doesn't spend such long times, but it does still spend a long time there. And the regions that separate the conformations, typically the trajectory spends very short times, which you can kind of see by seeing that the dots are now further spaced apart. Okay, so this is just another picture to show that these transitions between conformations are what many people are often interested in. So this brings up the concept of rare events. On the left, what you see is basically a very, very simple conceptual picture of an energy landscape. So the black line here, the curve, that's the graph of an energy landscape of an energy function V. And at the bottom, we have the state, the y-axis, we have energy. And let's just say for simplicity, we have 2 conformations, which are denoted by A and B, that correspond to areas of low energy. And this is intuitive because we know that nature wants to minimize potential energy. And quantities such as the free energy difference are of interest in statistical physics because they capture lots of information about reactions. I won't go into that because that's not my area of expertise. But the idea here is that the important idea is that we're interested in transitions between basins of low energy. So that's what we see on the left. And on the right-hand side, we see a single trajectory of a dynamical system. In fact, it's a stochastic dynamical system, which starts in A. So this is where we start off. And it bounces around A because it's receiving random perturbations from a heat bath. And after a while, it undergoes a very short but rapid transition to B, where it bounces around for a while, and then it goes back to A, and it stays there for a long time. So this simulation is very simple. I think it was done on MATLAB. It's about 300,000 time steps. We only observe one transition from A to B and one transition from B to A. So this just goes again to emphasize how rare these transitions of interest are. What we've done here, as shown, is that we're modeling the dynamics of this molecule in equilibrium with a heat bath using a stochastic differential equation driven by the gradient of the potential energy V. And we're using this Brownian motion perturbation to model the effect of the heat bath on the molecule. Okay, and beta inverse is like is a temperature. So beta is actually the inverse temperature. Okay, so this is the conceptual idea of what we're looking at. We're looking at stochastic dynamical systems defined by an SDE and a gradient of a potential. And in particular, our diffusion matrix is particularly simple. It's proportional to the identity. Okay. So another thing which I would like to quantify because to define, because it's quite important in what comes later, is that we're going to look at the first hitting time to this metastable set B. We've just chosen B for simplicity. It could have been A, whatever, but we're just going to fix a target set B. And we're interested in the first time that the system enters the state B. And that is essentially what tau of x is. Tau of x takes as an argument, basically a trajectory of your dynamical system x, and it tells you what's the first time that your trajectory first entered the set B. Of course, this is not completely specified because I haven't said, well, at time 0, where is what is x0? What's the initial condition? I'll do that later. But it's important to remember that tau of x is basically a first hitting time to a how should I say, a fixed metastable set B, or an energy basin B. Okay, so the goal is that we are given some kind of path functional W. And basically by path functional, I mean it's a function which you give it a trajectory or a continuous path, and it gives you a number. And given a path functional W, we're interested in one of the most basic questions, which is what is the expected value of W for when we give W the trajectory of this equilibrium system defined by this SDE that we saw before. Now, a simple Monte Carlo strategy is to basically use molecular dynamics or MATLAB, whatever, Euler-Maruyama, sample paths of your stochastic dynamical system. Then you have a whole bunch of trajectories, time series data. And from this, you compute for each trajectory the value of W of x. Then you take the sample values of x, take the average, and that's your Monte Carlo estimate of this expected value. Now, there's a problem here. If our path functional depends on the first hitting time to B, given that we know from before that sometimes this first hitting time can be really large, this introduces the problem of, this basically mixes the problem of rare events into Monte Carlo. Because we have rare events, because on average tau of x will be very large in expectation, this means that the Monte Carlo approach, the simple Monte Carlo approach, will tend to converge really slowly because you just have to sample so many trajectories to get one useful transition that you can then use in your Monte Carlo method. So this is the problem that we're trying to get around. Okay, so let me just make this a little bit more concrete, hopefully. There's a function called the B committer, or more simply the forward committer. I've defined it the B committer here because the set B is our target set. We've defined our stopping time or our first hitting time to be respect to B. So the B committer, QB of little x, is basically the probability that your system, your equilibrium system X, when it hits B, oh, sorry, this is, I realize I made a mistake here. Tau should be the first hitting time to either A or B. So basically, I've mixed up a little bit of the notation here, but what you should take away from this is that tau is the first time the system hits either A or B. So either the lower energy basin or the higher energy basin. And we're interested in the event that when it does hit either of these, it hits B. And you can formulate this probability as the expectation of an indicator function, given that, so when it hits either A or B, it's in B. And we're conditioning on the fact that the initial condition is little x. Okay, so what does this B committer look like? At the bottom here, you see the graph of the original potential, V, that we saw from the previous slide. The y-axis is V of x, and the x-axis here is the initial condition, little x. And again, we've got the lower energy basin A and the higher energy basin B. And as you might imagine, when you're really close to A, the probability of hitting B before A is really close to 0. Whereas as you rise up this energy barrier, it starts to increase. And of course, when you get closer to B, then your probability of hitting B before A is closer to 1. So basically, the B committer tells you what's the probability that I'll hit B before A, given that I start at some point X. Okay, so this brings us to a stochastic optimal control problem that I will present in this talk. That was kind of the motivation. Let's go back now to the SDE. We have an SDE that defines the equilibrium dynamics that we've seen from before. And now let's define what the path function of interest is. So I'm going to write it as work. It's not necessarily work in the physical sense, but it's just convenient to think of it this way. So the work done by the trajectory or the system up to the first time t of first entry into either B or A here, it's defined as basically an integral of a running cost function f, which we assume to be non-negative, plus a terminal cost function that basically we compute when we hit B, where are we on the boundary of B, then we evaluate this function g. So yes.
Why do you call it equilibrium dynamics?
That's a good question, because I call it equilibrium because that's our reference in some sense. This is what we assume that the molecule does if we don't touch it at all. And what I'm going to do later is I'm going to apply a force to it. I'm going to drive this molecule out of equilibrium.
Ah, I see. Mm-hmm.
So it's equilibrium because it's in equilibrium with the forces acting on it, which in this case are just the heat bath represented by the Brownian motion. And then later I'll add another force.
Okay. Mm-hmm. Thank you very much.
Thank you. Okay. Now, given this work path function,
what is the potential? Sorry, what is the potential function here in your simulation? Because I think it's important the role of the function, the potential function in your simulation.
Well, of course it is. It's important. So in molecular dynamics, this potential would be the sum of bond interactions, electrostatic potentials, what have you, Coulomb stuff. It's whatever you want. It will it'll typically have some kind of growth to infinity as you go further out. It won't be convex because otherwise then it would be very interesting. But for this presentation, I'm not going to go into any details about the potential. This is rather at a rather abstract level.
Thank you.
Okay, you're welcome. Any other questions? No? Okay, good, then we'll go on. So given this work path functional, let's define something which looks like a conditional free energy. And this is our quantity of interest. I'm going to define it as f of beta and x. Beta, recall, is the inverse temperature from the SDE. And x is the initial condition at which we start all of the trajectories of the system. And if you just look at this, basically it is it's a scalar, it's proportional to a conditional cumulant generating function of the work path functional w with respect to the law of the stochastic system x. And that's just a very probability theory way of describing what you're seeing here. Just minus beta inverse of log expectation of this exponential. So if you use Jensen's inequality, then we observe that minus the log is a convex function. So if we move this inside the expectation, it cancels the exponential minus beta. And what you get is something that, I guess, plays a role of a second law of thermodynamics. It says that your conditional free energy is a lower bound to the expected work that you do on this system. Of course, in statistical physics, you usually don't have this you don't have this conditioning on the initial condition. This is where we're doing a more, how should I say, mathematical presentation of this. We're trying to use some of the ideas from statistical physics, but we're not exactly doing statistical physics. Okay, so now this is where I go back to Hong's question. This is our equilibrium model from before. And now we're going to apply a force to it. We're going to apply a feedback control function, C, to the system. And by applying a force, we're driving the system out of equilibrium in some sense. And I'm now going to denote the controlled stochastic dynamical system by X superscript C. Before, the equilibrium model had no superscript. Whenever there's a superscript, it means that we're using some control. And the only thing we're changing in this SDE is the drift. The diffusion stays the same. Now, the problem is here, if we just use Monte Carlo averages of the non-equilibrium system, XC, the Monte Carlo averages will usually differ if C is non-zero because we're working with completely different random variables here. Instead of X, we're working with XC. So mathematically, what does that mean? If I am going to introduce a notation here, E superscript 0x, that's just defined to be the expectation with respect to the equilibrium system X. So zero control, that's why we have zero. And we're using X as a superscript to remind ourselves that we're starting all of our trajectories from little x. Now, this expectation here will be different from this expectation because, as mentioned before, X and XC are actually different random variables. And I'm going to denote by E superscript Cx, the expectation with respect to the controlled system or the non-equilibrium system. Okay, so yeah, this is just what I've said before, or mu Cx is the law of the controlled system, xc, conditioned on the fact that it starts at little x. Okay, so now—
sorry, just another quick question here.
Sure.
Yeah, so in this formulation, in the non-equilibrium formulation, so can I understand it as like you actually change the potential? You are doing a simulation for another potential?
Yes, that is what you can understand. And in molecular dynamics, people often do this. So there's a big area of molecular dynamics called metadynamics, where basically you have a potential, and at each state of where the system is, you add a small Gaussian. So basically if you start in a metastable, if you have this metastable energy basin, you start in a basin and you keep adding little Gaussians there. Eventually you're going to fill up this basin, and this will enable you to transition to the other basin. So C can be understood exactly as changing the potential.
Thank you. Yeah,
you're welcome.
Han, can I ask here, how do you choose C here? Is there any criteria here?
That's what we will come to later.
Okay, thank you.
Yes. Yeah, so in this work, we don't have a good a priori guess of what C should look like, and we're going to try and learn it, quote unquote. I'm not going to say deep learning, this is because that's not what we're doing, but we're going to try and do it in a gradient descent way. Okay. So now that I've introduced basically a whole family of probability measures, mu Cx, parameterized by the initial condition C, by the conditional condition X and the control C, or the force, the feedback force C. And now that we have this whole family of measures, mu Cx, what we can do is we can use importance sampling. And what does that mean? We want to find a feedback control C such that some rare event that's of interest to us with respect to the equilibrium measure, mu 0x, is not rare with respect to the non-equilibrium measure, mu Cx. And this is basically what importance sampling is about. If you want to do something with an original measure, but it's not efficient to do that, change to a different measure and apply some kind of reweighting. And although we won't do importance sampling, the idea of importance sampling is important in what will follow. So this part is probably one of the more mathematical slides of this talk. If you don't get everything, it's fine, but I'll just go through it quickly. So as I mentioned, in importance sampling, there's this concept of reweighting. If you're going to draw samples from a different probability measure, but you actually want to compute the expectation with respect to your reference measure, then you need to reweight your samples, each sample, to get an unbiased estimate for your true expected value. And in stochastic analysis, one reweighting that's really well known is an exponential martingale. What is this exponential martingale? It's an exponential of this term, m minus ct of z minus this term here. And if you're familiar with the notion of a Rado-Nikodym derivative, this is essentially the Rado-Nikodym derivative of the law of the equilibrium system with respect to the law of the controlled system or the non-equilibrium system. M minus ct is basically a stochastic integral. It's an Ito integral. You have the scaling of the inverse temperature here, and b actually here, this should be psi. So this is the Brownian motion. So this is just an integral with respect to Brownian motion. This is a continuous local martingale. And the angular brackets refer to what is known as the quadratic variation process. But what's relevant for us here is that basically it behaves like a kinetic energy term, whereby kinetic energy is basically the kinetic energy of the control, or if you want, the cost of control. Okay, so now we have all of these ingredients here. We know that the exponential martingale plays this role. We start off with our conditional free energy f beta of x. This is what it was defined to be. Now, using this reweighting here, we can rewrite this expectation as an expectation with respect to Cx, the non-equilibrium measure. But when we do that, we have to include the exponential martingale. This is just how the Rado-Nikodym derivative works. Now, again, we use Jensen's inequality. We bring the minus beta inverse log inside the exponential, and it will take care of the exponential here, and it'll take care of the exponential here. And up to a proportionality constant, which I've omitted here, what we now have shown is that our conditional free energy f beta of x is bounded from below by the expectation of the work W with respect to the non-equilibrium measure plus this cost of control term. And what I've absorbed here is basically a beta inverse term, okay? Right, so the stochastic analysis part comes here and here because we're using that this stochastic process is a continuous local martingale. So if I take its expectation for any little t, that's just going to be its initial value, which when you set t equals to 0, this is going to be 0. So good. Okay, so now what's our stochastical optimal control problem? Suppose we are given a bounded path-connected domain S in Rd, and we fixed some terminal set, some non-empty set B, which is a subset of S, and we've defined our stopping time with respect to B. Basically, this is the tau is the first hitting time of B in this problem. The stochastic optimal problem is as follows. We want to minimize this objective function of phi. Phi is a function of C, our feedback control, and it's parameterized by your initial condition, little x. And this is just what we saw before in this inequality that I showed you on the last slide. This optimal control problem has a constraint that basically we have to satisfy the dynamics of the non-equilibrium system, and our initial condition, it must be little x, which is some point in S, in our state space, in our domain S. Now, I won't go too much into the details, but there are some well-known properties of the optimal control. This problem, under certain assumptions, this problem does admit an optimal solution, which I'll denote by C-opt, namely that this quantity of interest, this conditional free energy, for any y in S, this is equal to your objective functional evaluated at the optimal control. Surprise, surprise. And what's interesting is that, in fact, your optimal control is proportional to the gradient of your conditional free energy. And this kind of goes back to the question that we had earlier about whether the control can be understood as a potential. And this gradient relation does indeed reinforce that notion that your optimal control will be kind of like a gradient of a potential. But what's interesting here is that the potential that we're taking the gradient of is the quantity that we are interested in. And this is nice because it kind of reinforces the connection to importance sampling. Some of you may know that in importance sampling, the optimal change of measure, or the optimal importance sampling measure, to know that, you actually need to know the quantity you want to know in the first place. So it's a little bit of a chicken and egg problem, and we have it again here. Okay, and these results you can kind of get from the PDE aspect of optimal control. You look at an HJB equation, a Hamilton-Jacobi-Bellman equation. I will not do that in this talk. Okay, so now we get to the question that Xiaocheng asked. How do we find this control? And one of the most basic approaches to solving an optimization problem is to use gradient descent. So what are we going to do? We choose finitely many basis functions, phi I, from I equals 1 to n, and each phi I is a function from our domain of interest S to Rd. Now we project our control to the span of these.
Oh, sorry, I just have another question. Actually, on your slide, I just try to understand your formulation. So, is your formulation? I assume it's in a fixed time, or I mean that the fixation happens in a fixed time in a given time, or
it's okay. That's a good question. So it's actually up to this random time tau here. So if you recall the work path functional W, it contains two parts, an integral up to tau and a terminal cost that happens when tau is active. So basically at time tau. So W, it depends on tau, and this quadratic variation or kinetic energy cost of the control, that also depends on tau. We evaluated the tau. So this optimal control problem is, I guess it's not a priori finite time horizon because tau doesn't have to be a priori bounded.
Okay.
It's basically the time, if you want to think of the motivation, it's what time do we enter a Bayesian, a metastable energy Bayesian B? And we don't have a priori bounds for that. So usually these things can be arbitrarily large.
First passage time or something like that?
You could think of this as a first passage time. People usually, for this specific type of optimal control problem, one has in mind a first exit time. So basically,
okay, first exit. Yeah, okay, yeah,
yeah.
Thank you. Yeah.
You're welcome. Okay, so back to this slide. How do we solve this optimal control problem? We choose basis functions. Of course, they have to be linearly independent. Then we project the control, which we don't know, to the span of these basis functions. So basically, we take our optimal control problem, which is in principle formulated over an infinite dimensional space, and we project it to a finite dimensional subspace. What does that mean? It means that the controls that we look for are parameterized by a coefficient vector A. So we just say that CYA is A1 phi 1y plus all the way to AN phi and y. And this is for any y in our domain of interest S. So what have we done? As mentioned, now we have a finite dimensional problem for a coefficient vector A. So this is our expansion coefficients with respect to this basis. And now instead of trying to find the optimal control C in a class of admissible controls, we just want to find the best vector, the best expansion vector A given this basis. And how do we do this? As mentioned, we use gradient descent or GD. We say that the iterate at discrete time n+1 of the coefficient vector is the coefficient vector at discrete time n minus some learning rate h of n times the gradient with respect to A of this function. So if you recall, phi here was the objective function of the stochastic optimal control problem. So in principle, phi will take a function. It doesn't have to take a vector, but we've transformed it into a finite dimensional optimization by considering only controls which admit an expansion with respect to this basis. Okay. And I guess in a lot of, you're all familiar probably with this concept of a learning rate. You can just think of it as a time step in a discretization of a gradient flow. Okay, so going back to the example of the B committer that we saw earlier, the B committer, just to recap and to make sure there's less confusion, hopefully, is basically the probability of hitting one set B before hitting another set A, conditional on starting at little x. So here the meaning of tau is slightly different from the previous slide. Sorry about that. And the work path function that we have, let's fix some positive lambda. It's just, we introduce this positive parameter for convenience because we don't want to take log of 0. Now our work path function is just minus beta inverse of log of this indicator function plus lambda. The exponential average is then this, if you just plug in W, and the conditional free energy just looks like this. Why is this important? Well, I'll just show you a toy model of what happens when we use gradient descent and when the conditional free energy that we are interested in is related to the committer by this formula. So you recall, this is a slide you've seen before. The top is the graph of the B committer, the bottom is the original potential V, and we have a low energy, a basin of low energy at A and a basin of low energy at B. And we're interested in the probability of hitting B before A, given that we start at some point X. Okay, so we're going to use gradient descent to solve this. We do this iteratively, of course, this being gradient descent. So at the top, you're seeing again the committer. The solid blue curve is the true committer, and the dashed blue curve is the approximate committer. And we're starting at 0. We're starting at a control of 0. So it means basically when we first do gradient descent, or at our very first iteration, we're actually sampling trajectories of the equilibrium system. We're applying 0 control and we see what happens. Then from the second iteration, we'll apply a non-zero control. At the bottom, what you see in this bottom figure here, the solid black curve is the potential that you get after optimal control. And the dashed black curve is the potential that you get with the control. And since we're starting at 0, what we're seeing here, the dashed curve is actually very similar to the uncontrolled potential. Okay, so we're doing gradient descent. We start at 0 and we keep doing this iteratively. And you can see that slowly the dashed curves move until they start getting closer and closer to the solid curve. And you might wonder, what are these artifacts? It's because I'm using a really simple collection of basis functions. The phi i's are basically gradients of Gaussians. So that's why you have these funny curves here. The basis is not particularly optimized for this problem. But the point of these pictures is just to show that gradient descent can work. Okay. And this is what you see if you just look at the plot of your objective function versus iterates. It starts out as not changing very much, and after a while it starts decreasing. The solid blue line is the true value for a given fixed x. And it's quite noisy, as you might see. Okay, so this is just a recap. This is how we solve our finite dimensional projection of the optimal control problem using gradient descent. Now, the mathematical question which I want to get to, and which this work is pretty much all about, is when can we be sure that basically our finite dimensional projection of the control or our approximation of the control C parameterized by A, when can we be sure that C of A converges to the optimal projection for any basis? And this is the question that we want to answer, because there was a paper some time ago which proposed this gradient descent algorithm for solving stochastic optimal control problems of this form, but it wasn't proven in that paper whether the gradient descent would always converge, or under what conditions would it converge. So the sufficient condition that you might guess is that, well, if our objective function of our optimal control problem is strictly convex, and if we follow the gradient down, then we will get to the minimum. We'll get to the unique minimizer of the functional phi. So basically, this brings us to a second derivative test for convexity, except in infinite dimensions. So now E is a real Banach space. U is a non-empty convex subset of E. And if F is a twice Gato differentiable function from U to R with second order derivative D to F, then F is convex if and only if its second derivative is always non-negative for any directions that you put. And if it's strictly positive for all non-zero V, then your function F is strictly convex. And this is what we're going to use in the next few slides. So for the next few slides, I'm going to set E, basically the directions in which I evaluate this Gato derivative, to be the set of all bounded functions from Rd to Rd. U is a convex subset of E that contains 0. Why do we want it to contain 0? Because we want our optimal control problem to still contain the reference measure, which is mu0x. Basically, when we don't apply any control, we still want to include that in our analysis. Okay, so as you might imagine, in order to obtain the derivatives, we need to do some kind of variational analysis. And I will do that in this slide, just for the work functional, this work path functional. Recall that the objective functional phi of the optimal control problem has two parts, an expected work part, and a cost of control part, or a quadratic variation part. Now let's look at this, the expected work component first. Under some assumptions, which I'm going to sweep under the carpet, the map that sends your control to the expectation of your work with respect to the control measure or the non-equilibrium measure, this map is twice Gato differentiable, and its first Gato derivative in the direction V takes this form. Basically, it's an expectation of your original work multiplied by a continuous local martingale term evaluated at the stopping time tau. And your second Gato derivative, evaluated at two directions, V and W, has a similar form. Why is this nice? As a corollary of this, you can say if for all C and X, so if for every admissible control C and for every initial condition X, if W is mu Cx almost surely bounded from below, then the map that sends your control C prime to the expectation of W with respect to C prime, this map is convex on U. And in addition, if W is not mu Cx almost surely constant, so basically there must be with some positive probability, W has to assume a different value from some other value, then this map is in fact strictly convex. Okay. So now we can also look further. We can go further to the objective functional, but to do that, we need to look at the cost of control part. Yes.
What is C prime?
C prime, it's just a placeholder. Here, I didn't want to write C. I just wrote C prime instead of C. It's not the derivative. Sorry.
Okay. Yeah.
Okay.
Thanks.
You're welcome. So now we can look at the cost of control. This is the map that sends the control to the cost of control term. Or if you want to think about it, this is also in fact related to the relative entropy or the Kullback-Leibler divergence of the control measure with respect to the non-equilibrium measure with respect to the equilibrium measure. I won't get into that here. But you can show that this map is also twice Gato differentiable. And if you can actually have a lower bound on the second Gato derivative evaluated at the same argument V and V. Why do we consider this? Because as you recall, this is relevant for the second derivative test of convexity. Okay, so now recall this is the form of our objective functional. Using this proposition and the corollary that we saw from the previous slide, we can show that if under certain conditions, if W is almost surely bounded from below and not almost surely constant, then in fact, your objective function for your non-projected optimal control problem, that is strictly convex on U. And I must I mean, in case this seems too clean, I will remind you that I've swept a lot of details under the rug here, because it's basically really technical and a bit dry, and I don't want to go too much into that. So what, basically? Well, the strict convexity of the map that sends your control to the objective function, and here I've forgotten a little x here, the strict convexity of this map on an infinite dimensional function space is what we've just proven on the previous slide. What is this useful for? Well, it implies that basically the finite dimensional projection of our functional is also strictly convex. It's a strictly convex function on Rn. And what does this imply? Well, this implies that your gradient descent iterates will converge to the optimal control given your fixed basis for any basis, up to any errors due to your discretization of your SDE and any statistical errors because we're using finite samples, basically. And the tools that we've used in here are basically variational analysis, as I've showed you before, Gato derivatives, so on and so forth. And under the carpet, there's a lot of stochastic analysis. I've hinted a little bit at the exponential martingales. And in fact, that brings me to the end of the talk, which is somewhat on time. And yeah, if you have any questions, please ask. Thanks a lot for your attention.
Thanks very much, Han, for the very interesting talk. Do we have any questions? Home?
Yes, so may I have two questions? So everything here depends on the temperature, right?
Yes.
So how do they behave with respect to the temperatures?
I see. So this is a part of the analysis that we have not carried out, because for this problem, what basically the motivating question for this work was to ask, when does gradient descent converge? And in practice, so yeah, in statistical physics, often you see people who they change the temperature during a simulation in order to sample rare events. That's a strategy which we are not looking at in this paper. So this analysis, how would it carry over to that? Well, from the stochastic analysis point of view, if you change the temperature, then what you are doing is you're changing the diffusion part of the SDE. And once you do that, then basically you can't use this approach because you don't have Radon-Nikodym derivatives.
And yeah, thanks. Another question is that if you want to I don't know, go to another. I mean, if you have different B, then you need to redo the algorithm, right? I mean, if you want to rig to another.
Yes.
Okay,
yes.
Then,
if you have a different terminal set B, if you change that, then yes, you have to do everything again. This is very specific because your hitting time or your first exit time tau is defined with respect to B. If you change that, then you change other things. So what's important to notice, and I can maybe go back to this, it kind of hints at it here, pardon me. So at this part, when I was looking at the optimal control is very specific to your conditional free energy F. And your conditional free energy it's not only defined by your set B, it's defined by your set tau and your running cost F and your terminal cost G. So if you change any of these, then F will change, and therefore your optimal control will also change.
I see. And another question, is it 1D or multi-dimensional setting?
Here, this is multi-dimensional. The pictures were in 1D because that's as far as I want to go regarding numerical work. But yeah, the analysis carries over for any finite dimensional SDE.
I see. Thank you very much.
Thanks for your question.
Yeah, actually, I have a couple of questions to ask too. Yeah, my first question is actually, I just want to understand this correctly. So this optimization is actually to kind of find the most probable path, right, for important sampling, right? So you haven't actually done important sampling, is that correct?
This is correct. So I think I did mention it at some slide. The important sampling, we use that as an idea. We use that as a basis for this change of measure idea. But we don't actually do...
Yeah, but you didn't actually change the measure, right?
No, we do. So that's the thing. When you apply a control, this is why there are this whole family of measures. So our reference measure, our equilibrium measure is mu 0x. That's the measure with respect to which we want to compute all expectations. That's like our truth. But this is not efficient because of the rare event problem. So what we're doing is that we're changing the measure. So in stochastic analysis, when you change the drift, when you add this control, you're changing the measure. You're now sampling, and then basically when you have trajectories of the controlled or the non-equilibrium system XC, you can still do Monte Carlo with that, but it'll be done with respect to a different measure. So there is a change of measure. And what I should also mention here, so where is it? The exponential. So in order to compute basically anything in your objective functional, you can compute everything that you need to do important sampling as well. Basically, once you computed MC, you in principle can also compute this M minus CT with little additional computational overhead. And once you have these two ingredients, you have this change of measure. So then with this change of measure, this Rado-Nikodym derivative, you can in fact do important sampling. And what I've shown you, this analysis regarding convexity, we don't actually do it.
Yeah. So suppose you are actually interested in the probability of let's say phase transition, you can actually apply this kind of additional step, right? So you apply important sampling to, you're able to actually calculate this small kind of transition probability.
Yes, you can. Yes, you can. Yes, you can.
Yeah. Yeah, thank you. And actually, another question, just try to kind of clarify. So it's like in order for the algorithm to converge, so basically the optimal path has to be unique, right? Or
so I noticed that you used the word optimal path. Here we're not looking for a specific trajectory in state space. We're looking for an optimal control, an optimal feedback control.
Okay.
So, right. We're not looking.
Like, I don't know. Is it like equivalent or no? It's not. Yeah.
I'm not sure it's equivalent. So I'm familiar a little bit with transition path theory, but which I think goes in the direction that you're looking at in terms of most probable paths and things like this. But
yeah, I understand that you are working on the control function, but I just feel like they may be in some sense. I'm not sure. I thought it might be equivalent, but but as you said,
as far as I'm aware, I don't think it is. Yeah, but it might be. I'm just not aware of any connection between optimal control and transition path theory. Of course, there's a Feynman-Katz PDE boundary value problem that appears in both, especially because of the committer. Maybe this is also one reason why one would think of the most probable path, but I don't think this machinery can be used for transition path theory.
Yeah, I see. That makes sense. Thanks.
In some sense, they are related, because when you apply the control, ideally what you would expect is the best control will give you the fastest path, right?
Yeah.
We don't look at that. We don't look at that here.
Okay. Yeah.
But thanks for your questions. That's interesting.
Yeah. Thank you.
Sorry.
Go ahead.
Does Gattuck's differentiability guarantee the convergence? Because I think we may approach in different direction to the solution, and maybe we need more stronger condition for example, pressure differentiability. Because if we approach to the solution in different directions, maybe we don't have the uniqueness of the solution.
Well, so what I've shown. Please, I'm not sure if you finished your question. Have you finished your question?
I mean, because you are approaching the solution in different directions, so maybe you not get the unique solution. And we may need, for example, pressure differentiability if we want to have the solution.
Okay, so what I've proved, the results that I've shown in the later slides are basically to show that this functional here, this objective functional, phi, so let's fix little x. And now we're interested in a map that sends a control C to the value of phi, C, and x. What the results in the later slides show is that basically this map is strictly convex, or if you want to say it, the functional phi is a strictly convex functional of C. And once you have a strictly convex functional of C, if you follow the gradient, which you've also shown that phi is a derivative, in fact, one can show that it is Frechet differentiable. But for the purposes of convexity, you only need Gato differentiability. And this is established.
Thank you.
You're welcome.
Do we have any further questions? I have a few quick questions for Han. So first of all, how do we choose those basis functions? Does that matter?
When you say the space of functions, do you mean the set U or the basis functions?
I think it's here. It's a phi I here.
Okay, this is very problem specific, right? And this is where you would need to know. Of course, one could choose any basis, but this might make the performance of your gradient descent optimal, more optimal, or better or worse, depending on how good your basis is. This is where you would need to have some kind of intuition about what does your energy landscape look like, and then you would try to choose the basis functions accordingly. Maybe using this idea from method dynamics to try and remove some Bayesians to make the transitions faster, for example. But a priori, this mathematical analysis does not. We tried to keep it rather general, so we didn't look at very specific problems.
Okay. If I may, how often do you have to solve this optimal control problem?
When you say how often, what do you mean?
So because for, let's say, for a typical molecular dynamic system using, let's say, Langevin dynamics or Brownian dynamics, for each time step, we have to evaluate the force and then update the trajectory, basically. But I don't know how often you have to solve this optimal control problem here, because you have this kind of optimization procedure in some of the other slides.
Yes. So I guess, yeah, here. It depends. It depends basically how often do you want to find the conditional free energy of some work path function. I'm not sure this is a satisfactory answer, but if from your question, basically, just to compute the gradient, for example, you would need to run many MD trajectories because this gradient is still an expected value of something, and you would approximate this using basically many trajectories, many MD trajectories, and for each trajectory you evaluate some quantity. Then you take the sample mean, and that's your approximation of this. Then you've done one gradient descent iteration, and you still haven't solved the optimization problem completely or within a desired tolerance. If I understand your question is saying how useful is this optimal control approach, that I cannot give you a good answer to that. Yeah.
Okay. May I ask one last question?
Of course.
By adding this additional term C, and do you actually change the inverted measure from the equilibrium system?
Yes.
You do. Okay.
Yes, you do. And this is why we refer to it as a non-equilibrium. So going back to a previous question, if you want to think of equilibrium measure as the true measure, the measure which you really ideally would like to be able to sample from, but it's difficult to do so. That has, as you mentioned, an invariant measure given by some Gibbs-Boltzmann density. And when you add a control, so typically one would choose the phi i's to be gradients of some potential-like functions. What you're doing is that when you add a control, you're also changing the potential. So once you change the potential, you're also changing the invariant density. Your non-equilibrium system will have a different invariant density compared to your original uncontrolled or equilibrium system.
So following on this, is there any guarantee that there will be another invariant measure different from the original one?
What do you mean? Because ultimately we still are interested in just one invariant measure. That's the invariant measure related to mu0x. We just use the other measures, mu cx, to get around this problem of rare events. But ultimately, what we still want to compute, the measure with respect to which we want to compute everything, or the true one, is basically still the true invariant measure.
Okay, fine. That's fine. do we have any final questions for Han? If not, thanks very much, Han, for your very interesting talk and for answering so many questions. It's a pleasure to have you here today. Thank you very much.
Thanks a lot.
Very interesting talk.